November 22, 1943. Occupied France. 1437. A Focke-Wulf FW190. Peeled hard left and opened fire. The cockpit of Lieutenant William Roach's P-47D exploded into chaos. Instruments shattering, compass spinning wildly, French farmland filling his windscreen where blue sky should have been. He yanked the stick. Nothing familiar came back. The horizon was gone. The radio was screaming static. And somewhere below him, through the torn clouds and diesel smoke of occupied Europe, a German airfield was waiting. He didn't know it yet. By the time Roach realized his mistake, that the runway lights below belonged to the enemy, not to England, it was already too late to climb back out. He put the Thunderbolt down on German soil with a sound like a freight train derailing. The aircraft skidded to a stop. German soldiers surrounded it within minutes. And one of the most powerful single-engine fighters ever built fell into enemy hands almost completely intact. That P-47 would be repainted, studied, flown, and dissected by the best engineering minds the Third Reich could assemble. What those engineers found inside it, and what they concluded after opening its engine, would quietly confirm what Germany's most honest officers had already begun to fear. That this war, when measured in horsepower and factory output, was already decided. But to understand why that captured aircraft shook them so deeply, you have to go back 3 years. You have to go back to a man on a train. A man almost nobody knew. A man who was about to design something that his own colleagues would call a dinosaur, and who was right about that, and right about everything else too. His name was Alexander Kartveli. He was not a general. He was not a politician. He was not even American by birth. He was a Georgian immigrant who had arrived in New York in 1927 with almost no money, almost no English, and one very specific ambition. He wanted to design aircraft. And in the summer of 1940, sitting on a commuter train somewhere between Washington and New York, he pulled out a single sheet of paper and began to draw. What he drew that afternoon would become the most produced American fighter of the entire Second World War. It would fly more than 546,000 combat missions. It would destroy nearly 12,000 enemy aircraft. It would kill more German tanks and locomotives and armored columns than any other Allied aircraft in the European theater. And it would do all of this while being described by the men who flew it as a flying bathtub. Kartveli was born in 1896 in Tbilisi, in the Caucasus region of what was then the Russian Empire and is now the country of Georgia. He studied aeronautics in Paris in the early 1920s at one of the most respected aviation programs in Europe, working in the orbit of Louis Blériot, the first man to cross the English Channel by airplane. When Soviet forces absorbed Georgia into the USSR, Kartveli had no home left to return to, so he came west instead. He came to America. He joined forces with another Georgian exile, Alexander de Seversky, and together they built the Seversky Aircraft Company on Long Island, New York. When de Seversky was eventually pushed out by the company's investors, Kartveli stayed on as chief designer under the renamed Republic Aviation. Quiet, methodical, precise. A man who said very little and drew extraordinary things. By 1940, the pressure on men like Kartveli was enormous and getting worse by the week. Combat reports from Europe were arriving in Washington with brutal clarity. American pilots flying American aircraft against the Luftwaffe were not surviving. The existing fighter designs, lightweight, nimble on paper, fatally compromised at altitude, were being torn apart in engagements over France and Britain. The Army Air Corps issued a new set of requirements that to most engineers who read them sounded less like a specification and more like a wish list written by someone who had never actually built an airplane. The new fighter had to reach 400 miles per hour at 25,000 feet. It had to carry at least 8.50 caliber machine guns. It needed armor around the pilot's self-sealing fuel tanks to survive battle damage, and the range to escort heavy bombers deep into the heart of Germany and bring them home. 2 of Republic's existing prototypes had already been canceled. The XP-44 and the original lightweight XP-47 concept were gone. The Air Corps didn't want lightweight. They wanted something that could do all of this simultaneously and survive doing it. Every other engineer in the American aviation industry looked at those requirements and reached for a pencil to start trimming the list. Kartveli looked at them and reached for the biggest engine he could find. The Pratt & Whitney R2800 double Wasp was in 1940 an engineering achievement of almost unreasonable ambition. Development had begun at Pratt & Whitney's facilities in East Hartford, Connecticut in 1936. The engineers took 2 rows of 9 cylinders and arranged them in a twin-row radial configuration, 18 cylinders total each one, displacing roughly as much as the entire engine of a 1940s family car. Total displacement 2,804 cubic inches, just under 46 liters. Right out of the gate when it entered production in 1939, the double Wasp produced 2,000 horsepower. That was its baseline, not its emergency output, not its war emergency rating with special fuel injection, its everyday starting point. Kartveli looked at that engine and made a decision that every senior engineer at Republic thought was insane. He decided not to design an airframe and then fit the engine into it. He decided to work in reverse. He would start with the engine. Then he would add a turbo supercharger, a General Electric turbine unit that used exhaust gases to pressurize intake air at extreme altitude, maintaining full engine power where thinner air would normally strangle performance. And then, and this is the part that made his colleagues genuinely question his judgment, he decided to design the ducting for that turbocharger first before designing any other part of the aircraft, and then build the entire airframe around the ducting. The turbocharger unit was roughly the size of a small washing machine. It went in the tail. The engine went in the nose. Hundreds of feet of stainless steel exhaust pipe had to snake through the belly of the fuselage, channeling hot gases backward from 18 cylinders to a turbine 19 feet behind the engine, then routing compressed air back forward through an intercooler to the carburetors. The total internal air journey, from nose intake to engine intake, was 43 feet. The cockpit sat directly on top of all of it, perched above a fuselage that was by any standard of 1940 fighter design grotesquely wide and deep. Kartveli told his colleagues, "It will be a dinosaur, but it will be a dinosaur with good proportions." They were not entirely convinced. The aircraft that came out of those calculations was enormous. It weighed more than 14,000 pounds, fully loaded, heavier than some twin-engine aircraft. Its fuselage was so deep that German pilots who saw it for the first time from a cockpit across the sky genuinely could not determine what they were looking at. British RAF officers, when they saw the first P-47s arrive in England in early 1943, were politely horrified. One joke circulated widely among the Allied squadrons. A Thunderbolt pilot under attack could defend himself by running laps inside the fuselage until the enemy gave up. Don Blakesley, one of the most experienced American fighter pilots in England at the time, flew an early model P-47C and delivered his verdict with characteristic bluntness. "It ought to be able to dive," he said. "It certainly can't climb." But on May 6, 1941, when test pilot Lowry Brabham lifted the XP-47B prototype off the runway at Mitchell Field in New York, for the first time, something happened that nobody had quite predicted. Oil burning in the exhaust duct filled the cockpit with thick smoke almost immediately. Brabham could barely see. He considered bailing out. He held on instead. He brought the aircraft down, climbed out of the cockpit, stood on the tarmac for a long moment, and then said, "I think we've hit the jackpot." He was not wrong. The turbocharger reached peak effectiveness above 27,000 feet, exactly where the Focke-Wulf FW190 and the Messerschmitt Bf109 were running out of mechanical supercharger performance and beginning to struggle. At those altitudes, the P-47 wasn't slowing down. It was accelerating. And in a dive, the kind of screaming near-vertical plunge that German pilots initially believed was the Thunderbolt's only military value, it could reach speeds that structurally impossible for its opponents to follow. German pilots learned this the hard way and stopped trying. On June 26, 1943, a pilot from the 56th Fighter Group named Robert Johnson had his P-47 ambushed over France by 16 Focke-Wulf FW190's simultaneously. His aircraft absorbed 21 cannon shells and more than 200 machine gun rounds. His cockpit shattered. His hydraulics failed. Fire broke out briefly. A German pilot followed him for miles over the English Channel, emptying every remaining round of ammunition into the aircraft in pass after pass. The P-47 refused to go down. Johnson crossed the Channel, landed in England, and climbed out. He went on to score 27 aerial victories, every single one of them in the same aircraft type that should, by every engineering calculation available to the Luftwaffe, have been at the bottom of the Channel. That durability was not an accident. It was not luck. It was the direct consequence of a design philosophy built around one fundamental assumption that 2,000 horsepower was enough surplus to carry everything that might keep a pilot alive, and that no performance advantage was worth more than the man in the cockpit coming home. And then, in November 1943, the Germans finally got their hands on one. Lieutenant William Roach's aircraft sat on a German airfield largely intact, waiting to be understood. The engineers who surrounded it didn't know yet what they were about to find inside that massive fuselage. They didn't know that what they were about to open would force them to write reports that their own government would quietly classify as defeatist propaganda. They were about to look inside the engine, and nothing they found there would reassure them. The P-47 Thunderbolt was on German soil, intact, waiting, and the engineers who surrounded it were about to open something they were not prepared to understand. But before we get to that moment, before we get to the room where Germany's best technical minds stared at an American engine and went quiet, we have to understand what was happening inside the Luftwaffe's own production lines in the winter of 1943. Because that context is what made the R2800 so devastating to look at. Not just as an engine, as a verdict. By November 1943, Germany had already lost more than 2,300 experienced fighter pilots on the Eastern Front alone. The men replacing them were finishing training programs that had been compressed from 210 hours of flight time down to under 110 because there was no fuel to spare for longer instruction. Factory output was being disrupted by Allied bombing raids with increasing regularity. Albert Speer, the Reich's armaments minister, was performing miracles of industrial reorganization, and German aircraft production was actually climbing. But the quality of what came off those lines was beginning to quietly deteriorate in ways that frontline mechanics recognized and frontline commanders refused to officially acknowledge. Germany was not losing the air war yet, but it was beginning to lose the argument about whether it could sustain the air war indefinitely. And then Lieutenant Roach's P-47 landed on a German airfield, and the argument became considerably more uncomfortable. The aircraft was assigned almost immediately to the Circus Rosarius, the Rosarius Circus, an extraordinary Luftwaffe operation run by Theodore Rosarius, an officer tasked with collecting, evaluating, and demonstrating captured Allied aircraft to frontline German units. Rosarius had assembled an impressive collection: Spitfires, Mosquitoes, P-38 Lightnings. Now he had a Thunderbolt. He had it repainted in Luftwaffe markings, given German instrumentation where possible, and ferried to the Rechlin Experimental Center for formal evaluation. The pilot assigned to fly it was Hans Werner Lerche. Experienced, analytically precise, a man who had flown nearly every frontline German aircraft and several captured types. His intelligence briefings before the flight were consistent with what the Luftwaffe had been telling its pilots since the P-47 first appeared over France in March 1943. The Americans built functional aircraft, mass-produced, adequate for their purposes. Inferior in agility and climb rate and the kind of refined engineering elegance that German aircraft represented. Nothing to be alarmed about. Fly it, note, the weaknesses report back. Lerche climbed into the cockpit at Rechlin on November 10, 1943, and began his pre-flight checks. The first thing he noticed was the cockpit itself. It was enormous. Not uncomfortably large, deliberately large. The instruments were color-coded, grouped by function sized for fast reading under stress. The seat was positioned to give clear sight lines. The control layout followed a logic that was entirely practical, and not at all elegant in the way that a properly organized workshop is not elegant, but is exactly correct. Lurche had flown the BF-109, a cockpit designed around performance margins so tight that pilots routinely described it as wearing the aircraft rather than sitting in it. This was different. This was a machine designed around the assumption that the man inside it would be tired, possibly wounded, possibly both, and would still need to operate it effectively for 8 hours. He started the R2-800. The engine caught immediately and settled into a smoothness that Lurche would note specifically in his written assessment. Not the strained, purposeful vibration of a German engine running at the edge of its tolerances. A different quality entirely. A smoothness that communicated without any instrument confirmation that the engine was operating well within its limits, that it had margin to spare. He sat for a moment with his hands on his knees and listened to it idle. Then he pushed the throttle forward. At 2,000 horsepower, the acceleration was immediate and violent, in the way that only truly powerful aircraft are violent. Not a lurch, but a sustained, relentless push that did not diminish as the airspeed climbed. He climbed to altitude. The turbocharger came into its operating range above 20,000 feet, and the engine note changed, and the aircraft stopped feeling heavy and started feeling fast. At 27,000 feet, he ran the speed checks. The numbers came back. He ran them again to confirm. He brought the aircraft down and taxied in. He sat in the cockpit for approximately 2 minutes before climbing out. The ground crew watching him said later that his expression was not easy to read. He walked directly to a table, sat down, and began writing. His assessment, when it was completed and circulated through Luftwaffe technical channels, contained a sentence that required a certain kind of professional courage to put on paper in the Third Reich in November 1943. The Americans have not built a crude aircraft. They have built a practical one. He elaborated. The cockpit designed for long missions. The controls engineered for function over elegance. The engine built not to the edge of what was metallurgically achievable, but to a standard of reliability and repairability that assumed it would be used hard frequently and by mechanics who needed to fix it quickly between sorties. This was not the assessment of an inferior product. This was the assessment of a different philosophy, and in several measurable respects, a more effective one. But it was what happened when German engineers opened the R2800 itself that moved the evaluation from uncomfortable to genuinely alarming. The machining was the first thing. German engineers were accustomed to precision manufacturing. German industry had its own formidable traditions of tolerance and exactness. What they were looking at inside the double Wasp was precision at a scale they had not seen. The 18-cylinder barrels were uniform to a degree that spoke of tooling infrastructure operating far beyond wartime emergency production. The cooling fins machined directly from the cylinder head, forgings thin, tightly spaced, consistent represented a manufacturing technique that required capital investment in precision tooling that Germany's strained aviation industry could not have replicated in 1943, even with unlimited motivation. The crankshaft stopped them completely. Pratt and Whitney's engineers had spent nearly 4 years perfecting it, working through the punishing stress patterns of an 18-cylinder firing sequence before arriving at a design that could sustain full output without failure at combat temperatures. What the Germans were holding had no visible shortcuts, no simplified joints, no evidence of material substitution. The metallurgy was correct in every detail and clearly had been correct since the first production unit. There was no degradation visible between early and late production components, no sign that quality had been traded for volume as the war progressed. There are no compromises in this engine, one engineer wrote in a technical memo that would later be archived and largely ignored by his superiors. Every component has been built the right way, not the expedient way. We cannot say the same of our current production. Then they found the modularity. Individual cylinders could be removed and replaced in the field without disassembling the entire engine. For an aircraft flying 2 or 3 combat sorties per day, this was not a convenience feature. It was a statement about how the Americans understood the relationship between engineering and operational reality. German engines of the same era required extensive disassembly for comparable repairs, hours of work that grounded aircraft that could have been flying. The R2800 had been designed on the assumption that battle damage was a routine maintenance condition, not an exceptional one, and that the aircraft should return to combat as quickly as possible after sustaining it. One of the engineers asked a direct question in the session summary. Could Germany replicate this engine? The answer that came back from the material specialists was equally direct. The high-temperature steel alloys required for the turbocharger turbine and ducting were not being produced in sufficient quantities. The precision bearing and compressor wheel manufacturing required for the turbocharger system exceeded what German factories could consistently achieve at mass production scale in 1943. The aluminum required for the airframe's substantial quantities uncompromised quality was a resource Germany was already rationing, substituting lower-grade materials wherever specifications allowed. But the question that really mattered was not whether Germany could replicate the R2800. The question was whether Germany could replicate 125,000 of them. Because that was how many Pratt and Whitney would eventually build manufactured not just at East Hartford, but by Ford Nash Kelvinator and other American companies that had retooled from civilian production and were maintaining identical precision standards at accelerating volume. The same engine that powered the P-47 also powered the Grumman F-6F Hellcat, the Vought F-4, U Corsair, the Martin, B-26, Marauder. One engine Type 4 frontline aircraft, over 100,000 units produced. Germany built approximately 28,000 BMW 801 engines across the entire war. The Americans built more than 4 times that number of a single more powerful engine type. That ratio was not a production advantage, it was a different category of industrial existence. The engineers at Rechlin, who understood what those numbers meant, were looking at something that had no tactical answer. You cannot outfly a production line. You cannot develop superior tactics against a country that loses 2 aircraft and replaces them before the sun goes down. The P-47's kill-to-loss ratio in aerial combat would eventually reach 4.6 to 1 for every Thunderbolt lost to an enemy fighter. 4.5 German aircraft were destroyed. The 56th Fighter Group alone would be credited with destroying more than 1,000 German aircraft against a loss of 128 of their own. An exchange ratio approaching 8 to 1 sustained over 2 years of combat by an aircraft that British pilots had initially described as too big to fight in. The reports from Rechlin were written classified and filed. Some of the engineers who wrote them were quietly reassigned. The ones who committed the most honest assessments to paper were in the bureaucratic language of the Reich's Aviation Ministry, spreading analyses inconsistent with operational confidence. No action required on the technical conclusions. Continue current production programs. It was perhaps the most expensive filing decision in the history of modern warfare. Because while those reports were being archived, Republic Aviation's plants at Farmingdale, New York and Evansville, Indiana, were accelerating. The final production count of the P-47 Thunderbolt across all variants would reach 15,683 aircraft. That single figure exceeds the combined wartime production of the Messerschmitt Bf-109 and the Focke-Wulf FW190 together. One American aircraft company. One aircraft type. More units than both of Germany's primary frontline fighters combined. And the quality held. Late war R2800 engines were not inferior to early war R2800 engines. They were more powerful and better refined. American factories were not degrading under production pressure. They were improving as their workers gained experience and their supply chains matured. Germany experienced exactly the opposite progression. Late-war German aircraft showed simplified joints, inconsistent material quality, occasional catastrophic quality, control failures that no amount of pilot skill could compensate for. Hans Werner Lerche's assessment of the captured Thunderbolt was accurate in every technical detail. What it could not fully capture, what no single evaluation flight could capture, was the weight of what sat behind that engine. A continent that had never been bombed, factories that had never been interrupted, raw material reserves that had never run short. A manufacturing civilization operating at full capacity with no intention of stopping turning out engines and airframes by the thousands, while Germany counted its remaining aluminum and shortened its pilot training programs and filed the honest reports in a drawer. The aircraft that Alexander Kartveli had drawn on a sheet of paper on a train in the summer of 1940 was by late 1943 not just a fighter. It was a demonstration. A flying proof of what happens when a country decides to build something correctly without compromise at unlimited scale. But Germany was not finished. And the men who refused to accept what those Rechlin reports were saying were about to make one final attempt to change the equation. They had a new aircraft coming. They had a new engine coming. And they had pilots who were still by any measure among the most skilled and lethal aviators in the sky. The question was whether any of it would be enough, and the answer to that question was going to be written in the spring of 1944 in the skies above Germany itself. The engineers at Rechlin had written their reports. The reports had been filed, and the Luftwaffe went back to war pretending the conclusions inside them didn't exist. But the P-47 didn't care about what Germany chose to believe. It kept flying. It kept fighting. And by the spring of 1944, the numbers coming back from the front were making the Rechlin assessments look conservative. Germany had lost over 800 experienced fighter pilots in the last 4 months of 1943 alone, men with hundreds of combat hours, men who could not be replaced by the shortened training programs producing their successors. The exchange rate was becoming structural, not a bad month, a permanent condition. And now with the American strategic bombing campaign deepening and the P-47 ranging further into German airspace than the Luftwaffe's planners had calculated possible, a more urgent question was moving up the chain of command. How do you fight something you can't catch at altitude and can't kill in a dive? General Adolf Galland, commander of the Luftwaffe's fighter arm, understood the problem with painful clarity. He had been asking Berlin for the Me-262 jet fighter since mid-1943. He had been told repeatedly that production priorities lay elsewhere, that the conventional fighter force was adequate, that his concerns reflected a failure of operational confidence rather than a genuine capability gap. In private correspondence that would later be recovered by Allied intelligence, Galland described the situation with a bluntness that matched Lerche's Rechlin assessment almost word for word. The Americans were not flying superior pilots. They were flying superior machines in superior numbers. Tactical excellence could not indefinitely compensate for industrial arithmetic. What the Luftwaffe could do, and did with considerable skill, was adapt its tactics. German fighter controllers began directing intercepts specifically to medium and low altitude, where the P-47's turbocharger advantage diminished and the FW190's agility could be brought to bear. They developed the bounce from above diving attacks at high speed that traded altitude for a single firing pass, then extended away before the Thunderbolts could respond. They targeted stragglers. They targeted aircraft with battle damage already visible. They learned quickly not to dive away from a P-47 and not to follow one above 25,000 feet. They were making adjustments the way a skilled boxer adjusts after the first round intelligently, professionally, and in full awareness that the man across from him hits harder than anticipated. The German loss rate slowed slightly in early 1944 as these new tactics took hold. February and March saw brief periods where Luftwaffe intercepts achieved respectable exchange ratios against the bomber streams and their escorts. For approximately 6 weeks, there were officers in Berlin who looked at the weekly loss summaries and allowed themselves cautious optimism. Then came April 1944, and the optimism ended. The problem was not German tactics. German tactics had adapted appropriately. The problem was that American tactics had also adapted, and the Americans had Francis Gabreski, David Schilling, Robert Johnson, and Hubert Zemke to do the adapting. The 56th Fighter Group had been flying the Thunderbolt since its introduction into combat, and had accumulated more institutional knowledge about what the aircraft could and couldn't do than any other unit in the European theater. Zemke's fundamental tactical insight that the P-47 was not a dogfighter, but an energy fighter, and that energy fighting at extreme altitude, followed by slashing dives, was its natural language had been refined through 14 months of combat into something approaching a science. But it was the specific mission parameters of the strategic bombing campaign that truly revealed what the Thunderbolt had been built for. April 8, 1944. Mission Briefing. Halesworth Airfield, Suffolk, England. 05:45 hours. The 56th Fighter Group was tasked with providing close escort to B-17 flying fortresses, attacking aircraft manufacturing facilities at Brunswick, Germany. Deep penetration mission. Round-trip distance approximately 900 miles. The P-47's assigned carried external drop tanks to extend their range. Briefing weather broken cloud cover at 15,000 feet clearing above. Anticipated German response heavy. The target was not incidental. Brunswick was one of the remaining centers of German fighter production. The Luftwaffe would not ignore it. Zemke led the formation up through the cloud layer and out into clear sky above 20,000 feet at 0730. The bombers were ahead and below their contrails marking white lines across the blue. The P-47's climbed to 28,000 feet and took up their escort positions. German radar tracking had been following the formation since the Dutch coast. The first vector came through German fighter control at 0815. Two Gruppen of FW190A8S, approximately 60 aircraft, were directed toward the bomber stream from the north. A third formation of Bf-109G6 was positioned further east to catch any escorts that had extended beyond their fuel range. It was a sound tactical plan. It had worked before. At 0840, the German fighters descended through the cloud layer and found the bomber stream, and found the 56th Fighter Group waiting at altitude above them. Zemke called the bounce. 16 P-47's pushed over simultaneously from 28,000 feet. They came down at over 500 miles per hour in near-vertical dives engines, screaming the turbocharger maintaining full pressure. The 8.50 caliber guns charged and ready. The FW190 pilots below had approximately 4 seconds of warning before the first firing passes hit their formation. 4 seconds is not enough time to brake effectively at combat speed when the attack is coming straight down from directly above. The first pass destroyed 6 German fighters. 6 aircraft in one coordinated firing passed the combined rate of fire of 128 machine guns delivering more than 400 rounds per second into a formation that had no angle from which to defend simultaneously. 3 pilots never recovered from the initial hits. 2 managed to bail out. 1 went straight in. The surviving German fighters split in every direction. Standard procedure: break the formation, deny the Americans coordinated targets, reform at lower altitude. It was the correct response. But breaking meant losing altitude, and losing altitude meant the FW190's were now at 18,000 feet with P-47's above them, which was precisely the geometry Zemke had been designing his tactics around for 14 months. The engagement lasted 31 minutes over the Brunswick area and the surrounding countryside. 31 minutes of diving attacks, climbing reversals, extended pursuits, and the brutal arithmetic of 8 guns firing simultaneously at aircraft that had only 2 responsive options: maneuver or run, and limited ability to do either effectively against an opponent with both superior altitude and superior straight-line speed. The 56th Fighter Group was credited with 23 confirmed aerial victories that day. Two P-47s were lost, one to a collision during a turning engagement, one to battle damage that proved fatal over the North Sea on the return. 23-2. The bomber stream reached Brunswick. The target was struck. Damage assessment photographs showed the manufacturing facility's main assembly hall destroyed, and two secondary buildings heavily damaged. The German pilots who landed that day and were able to write their after-action reports described something consistent with what Luftwaffe pilots had been reporting for months, but with a new emphasis on the hopelessness of the altitude equation. Once they are above you, one Gruppe commander wrote, there is no effective counter available with current aircraft. He did not recommend new tactics. He recommended the Me-262. He was not the first officer to do so. He was not the last to be ignored. The April 8th engagement was not the largest aerial battle of the war over Europe. It was not the most dramatic single mission in the P-47's record. But it was representative of what was happening across the fighter force with increasing consistency through the spring of 1944. The 56th Fighter Group's cumulative total by the end of April stood at 674, confirmed aerial victories against 58 losses, a ratio that operational analysts on both sides of the Atlantic recognized as historically extraordinary for a sustained campaign. The Luftwaffe's total pilot losses in the first 4 months of 1944 exceeded 1,000 men. Not aircraft men. Experienced, irreplaceable men whose accumulated combat knowledge represented years of training and operational learning that abbreviated wartime instruction programs could not reconstruct. German aircraft production under Speer's reorganized system was actually producing more airframes in 1944 than in any previous year of the war. The aircraft existed. The pilots to fly them with adequate skill were being consumed faster than they could be produced. This was the asymmetry that the Rechlin reports had been trying to describe. Not that German aircraft were inferior. The FW190D9, that began appearing in late 1944, was by most measures the finest piston engine fighter Germany produced, competitive with or superior to the P-47 in several performance categories. Not that German pilots were less skilled. The men of JG-2 and JG-26 defending the western approaches were among the most experienced and capable aviators in the world. The asymmetry was simpler and more brutal than any equipment comparison. America was producing trained pilots faster than Germany could kill them. Germany was losing trained pilots faster than its training system could replace them. The curve had crossed sometime in late 1943 and was now diverging at an accelerating rate. By the time Operation Overlord launched on June 6, 1944, the Luftwaffe flew approximately 170 sorties over the Normandy beaches on the first day. The Allied air forces flew over 14,500. The ratio was not the product of a single technological advantage or a single tactical innovation. It was the accumulated output of a manufacturing civilization that had been operating at full capacity since 1940, producing aircraft engines, pilots, and fuel without interruption, improving its processes as it scaled, and never once running short of the raw materials to continue. The P-47 over Normandy transitioned almost seamlessly from strategic escort to tactical ground attack. Its 8.50 caliber guns, its bomb load of up to 2,500 pounds, and its extraordinary structural resilience made it the ideal instrument for the low-altitude, high-risk work of interdicting German supply lines, armor columns, and troop concentrations behind the front lines. It flew in conditions low altitude, intense ground fire, close support of advancing infantry that would have been operationally catastrophic for aircraft with less structural margin and less engine resilience. From D-Day through the end of the war in Europe, P-47 pilots claimed the destruction of 86,000 railroad cars, 9,000 locomotives, 6,000 armored fighting vehicles, and 68,000 trucks. On a single day in July 1944 during Operation Cobra, one P-47 group caught a German armored column trapped between American ground forces and worked it continuously from mid-afternoon until after sunset. Ground investigation afterward found 66 tanks, 204 vehicles, and 11 artillery pieces destroyed. One group. One day. Alexander Kartveli, at his desk at Republic Aviation in Farmingdale, received the operational reports as they came in. He had known the aircraft was capable of this. He had designed it to be capable of this. The surplus horsepower he had built in from the beginning, the margin that his colleagues had called wasteful, that British pilots had called excessive, that German engineers had quietly recognized as something they could not match, was exactly what was enabling a single aircraft type to function simultaneously as a high-altitude escort fighter, a dive bomber, a ground attack platform, and a low-altitude close support aircraft without being optimally configured for any of them and adequate for all of them. The dinosaur, as he had predicted, had good proportions. But the story of the P-47 and the man who drew it was not finished. Because the aircraft's record in combat, the 546,000 sorties, the 12,000 enemy aircraft, destroyed the staggering ground attack numbers, was only the visible part of what Kartveli's train ride in 1940 had produced. The deeper legacy was something that would unfold over decades in peacetime in ways that neither Kartveli nor the men who flew his aircraft could have fully anticipated in the winter of 1944. What happened to the man who designed it? What happened to the engine that powered it? And what does the story of a Georgian immigrant drawing on a train actually tell us about why some ideas survive long enough to matter? That is the question. Part 4 answers. And the answer is not what most people expect. The war in Europe ended on May 8, 1945. The war in the Pacific ended 3 months later. And somewhere in the quiet that followed the sudden disorienting quiet after 6 years of industrial killing, a Georgian immigrant sat at a drafting table in Farmingdale, New York, and began drawing again. Alexander Kartveli had watched his aircraft fly 546,000 combat sorties. He had read the kill tallies and the ground attack assessments and the pilot survival reports. He had received the production figures from Evansville and Farmingdale, 15,683 Thunderbolts total, more than any other American fighter of the war. He had been told by men whose opinions he respected that the P-47 had contributed materially to shortening the war in Europe. He accepted this information with the same quiet precision with which he approached everything. He did not give speeches. He did not seek interviews. He went back to his drafting table and started drawing the next aircraft. That was who he was. Not a man built for celebration. A man built for the next problem. The recognition came in its official forms. Republic Aviation honored him. The American Institute of Aeronautics acknowledged his contributions. He received awards from organizations whose names meant a great deal to the engineering community and very little to anyone else. He became a citizen of the country he had arrived in with almost no money and almost no English in 1927, and he seems to have found in that citizenship something genuinely satisfying, not as a conclusion, but as a confirmation of something he had already been living for 2 decades. He had come to America to design aircraft. He had designed aircraft. The country had used them. The arrangement had worked. The men who had doubted the P-47 in its early months had largely stopped doubting it by 1944. Don Blakesley, who had announced flatly that the Thunderbolt could dive but certainly couldn't climb, eventually flew it to a personal kill tally that left the earlier criticism looking like a first impression error rather than a considered judgment. The RAF officers, who had politely informed their American counterparts that they appeared to be about to die in an oversized bathtub, had watched P-47 pilots accumulate kill ratios that their own Spitfire units would have been proud of. The institutional skeptics. The men who had pushed back on the design's weight and size and fuel consumption had been answered not by argument, but by mathematics, by the simple, irrefutable arithmetic of aircraft destroyed versus aircraft lost. Robert Johnson, who had absorbed 21 cannon shells and 200 machine gun rounds over France, and come home anyway, finished the war with 27 aerial victories and the Air Force Cross. Francis Gabreski, the highest-scoring American ace in the European theater, scored all 28 of his confirmed kills in the P-47 before being shot down in August 1944, not in combat, but when his propeller clipped the ground during a strafing run, an ending so mundane that it seemed almost inappropriate for a man of his record. He survived the war as a prisoner. He came home. He continued flying. The aircraft had protected him long enough to make a mistake and survive that too. But the true measure of what Kartveli had built was not in the individual stories as extraordinary as those stories were. It was in what happened to the technology after the guns stopped firing. The R-2800 double Wasp did not retire when the war ended. Pratt and Whitney had built an engine so fundamentally sound that the civilian aviation industry recognized its value immediately. The Douglas DC-6, which became one of the primary long-haul airliners of the early post-war period, flew on R-2800s. The Convair 240 flew on R-2800s. The Martin 404 flew on R-2800s. The same engine that had powered escort fighters over Brunswick and strafing runs over Normandy was now carrying passengers from New York to Los Angeles. Its extraordinary reliability in combat translating directly into the kind of operational dependability that airline accountants required and passengers took for granted. The last R-2800 engines came off the production line in 1960. 24 years after development began, 21 years after the first production units were delivered. More than 125,000 were built in total. Some of them are still flying today in restored warbirds and museum aircraft, producing that deep, slightly uneven barrel-chested rumble that no jet engine has ever replicated, a sound that builds in your chest before it reaches your ears. The turbocharger technology that Kartveli had built his entire airframe around became the foundation of modern aviation propulsion in ways that extend far beyond piston engines. The principle of using exhaust gases to maintain pressure and power at altitude, the principle that German engineers at Rechlin had correctly identified as something they could not replicate at scale, is the operating basis of every turbocharged and turbofan engine in service today. Every commercial airliner currently flying uses a direct descendant of the engineering logic that Kartveli incorporated into the belly of a fighter aircraft because he understood that altitude performance was not optional. The specific metallurgical and manufacturing advances that made the American turbocharger possible in 1941, while Germany's remained theoretical, were the same advances that made jet-age aviation possible in the decade that followed. Kartveli himself continued designing. The F-84 Thunderjet, Republic's first jet fighter, entered service in 1947 and flew in Korea. The F-105 Thunderchief became the primary American strike aircraft in the early years of Vietnam, the largest single-seat, single-engine combat aircraft in history. At the time of its introduction, a machine that carried more ordnance than a World War II B-17 bomber. And then decades later, the design philosophy that Kartveli had established, build around the mission, carry everything the pilot needs, prioritize survivability over elegance, reached its ultimate expression in an aircraft that is still flying combat missions today. The A-10 Warthog, which entered service in 1976 and has refused to be retired through 4 decades of attempts by budget analysts who find it insufficiently sophisticated, is in direct philosophical lineage with the P-47, built around its weapon system, brutally tolerant of damage, designed on the assumption that the pilot coming home matters more than the aircraft's theoretical performance ceiling. Kartveli did not live to see the A-10 fully vindicated in Gulf War service. He died in 1974, but he had established the argument in 1940, and the argument kept winning. Here is the lesson that the story of the P-47 actually teaches, and it is not primarily a lesson about engineering. It is a lesson about what institutions do with ideas they cannot immediately validate. The Army Air Corps canceled 2 of Republic's prototypes in 1940 because they didn't meet requirements that the combat reports from Europe had made obsolete. That was the correct decision made for the right reasons, but the replacement requirements they issued 400 miles per hour at 25,000 feet, 8.50 caliber guns, pilot armor, self-sealing tanks, escort range were judged by most of the engineering community as impossible to satisfy simultaneously. The standard institutional response to impossible requirements is to negotiate the requirements downward. Kartvel's response was to find an engine with enough power to make the impossible achievable, and design everything else around it. The difference between those two responses is the difference between the aircraft that got built and the aircraft that didn't. Every system that eventually defined the P-47, the R-2800, the turbocharger, the 8-gun armament, the structural resilience was at some point described as excessive, impractical, or wasteful by someone with institutional authority. Every one of those objections was answered not by argument, but by performance data. The aircraft flew. The pilots came home. The numbers accumulated. And the accumulating numbers gradually silenced the objections in a way that no engineering brief ever could have. This pattern repeats throughout military history with sufficient regularity to constitute something approaching a law. The tank was described as an expensive novelty by cavalry officers who had spent their careers mastering a different form of mobile warfare. Radar was resisted by commanders who trusted their observers and found the technology unreliable in early tests. The aircraft carrier was considered a secondary platform by admirals whose professional formation had been built around the battleship's 14-inch guns. In every case, the institutional resistance was not irrational. It was based on genuine experience with genuinely different conditions. And in every case, the resistance was ultimately answered by combat results that could not be argued with. The R-2800 built in 1944 was measurably better than the R-2800 built in 1942. American factories improved under production pressure while German factories degraded. This is the industrial fact that underlies everything else in the P-47 story, and it is the fact most likely to be overlooked in accounts that focus on aircraft performance specifications and aerial tactics. The quality held. At 100,000 units. At 125,000 units. In plants that had been building cars 18 months before they were building aircraft engines. The infrastructure of a peacetime manufacturing civilization, redirected with purpose and precision, turned out to be worth more in sustained warfare than any single technological advantage or tactical innovation. Now here is the detail that most accounts leave out, the detail that completes the picture, in a way that changes how you understand the entire story. When William Roach landed his P-47 on a German airfield in November 1943, he survived the war as a prisoner. He was repatriated in 1945. The aircraft he had accidentally delivered to the enemy, the aircraft that German engineers at Rechlin dissected and assessed and wrote honest reports about, that were then quietly filed and ignored, that specific aircraft was eventually destroyed in an Allied bombing raid on the airfield where it had been stored. The Germans never finished their full technical analysis. The reports that were completed were inconclusive in several areas because the aircraft was no longer available for follow-up examination. Which means that the most honest assessment the Luftwaffe's engineering corps ever produced about why they were losing the air war over Western Europe was based on incomplete data. They saw enough to know the conclusion. They didn't see enough to fully document it. And the documentation that did exist was classified as defeatist and removed from circulation. Germany lost the air war over Western Europe for many reasons, but one of the most consequential was this: the men who understood the truth clearly enough to write it down were prevented from making that truth actionable. The P-47 didn't win because it was perfect. It won because the country that built it was willing to hear the honest reports, act on them, and keep building. From a single sheet of paper drawn by a Georgian immigrant on a train in the summer of 1940 to 15,683 aircraft, 546,000 combat sorties, and a kill ratio of 4.6 to 1 sustained across 2 years of the most intense aerial warfare in history. Kartvel's proved that the most dangerous thing a country can build is not a weapon, but the industrial and institutional willingness to build it correctly at scale without stopping. The dinosaur had good proportions. It turned out that was enough. If this story stayed with you, leave a comment with another piece of engineering that changed a war. There are more of them than most history books admit. Subscribe because the stories that shaped the world we live in are almost never the ones we learned in school. And remember, every idea that changed history was at some point the one that someone in the room called crazy.